Hey Lewis, how you doing?
Good yourself.
Good, good. Glad we could meet for the study session. Congrats on getting the weekly winner.
All right, thank you, thank you.
How's everything been going so far? How's the studying going?
It's going well. So start getting to do some practice exams. Your study material is helping me a lot. So I scheduled my exam for next month,
Next
end
month.
of
Great.
March. So we'll see.
Great. What
So
about
far, so good.
so far so good? Is this your first time taking the exam?
It'll be my first time. Yes.
First time. Wonderful. And everything's been working out for you so far, doing the 8 hour once a week, trying to be active on the message board, keeping an index of wrong problems, all that good stuff.
Yeah, yeah. Trying to I'm trying to keep up with the work and personal life and study. It's hard.
Yeah, it's a lot. I like to think of it as, this will probably be the last hardest test you ever take, and once you pass it, it's keeping your license easy, right? As long as you
That's
don't
true.
end up with any disciplinary action, which is, pretty easy,
Yeah.
just doing what you're supposed to. The continuing education side of it, depending on what state you're in, most states require it, but the continuing ed is no big deal, keeping up with it. And we're doing those OMGuru seminars now twice a month
Yeah.
anyways, where it's like, I think I need 18 hours this renewal cycle, and I think I already racked up like 30 just hosting those
Oh,
seminars. So yeah, it's a ton of work. It's a huge sacrifice, but once you got it, I mean, it's pretty much yours for the rest of your career, which is the good news.
it's true. That's true. Yeah.
Cool. Looks like we got about 24 people hanging out with us. If you're in here following along, say hello in the chat. We'll be getting started here in just a few moments. Any questions before we get started or anything like that?
No,
Okay. And were you
I
able
did.
to go
Yeah,
ahead?
I did go over the PDF that you sent and all that material. Was helpful.
Good,
Um,
good, good. Yeah, that's the same. Pretty much, I just pulled all the practice problems you wanted to review. I just pulled them from each practice exam, and I
yeah.
lined up the solutions right after the problems. Yeah, it's that PDF. It's the same. It's the same PDF I'll be working from. And in
Okay.
fact, I'll share my screen now.
Sure.
Let's wake up the calculator. Great. So yeah, we can go ahead and get started. We'll go for the next hour or so. Um, do you want to start with those phasor diagrams of the synchronous motors and generators before the practice problems?
Yeah, we should. Yeah, we can start on that one.
Okay. And I know in your email, it sounded like you're most concerned with trying to correctly identify which ones belong to the generators and which ones belongs to the motors.
Correct.
Okay.
Um, Actually, more on the reactive when it goes to the reactive part. Kind of confused when the motor lead uh, or the generator leads or vice versa.
Sure.
Um, that's my doubt.
Okay. How about, do you want to skip the part talking about identifying which ones are motors and generators, or would you still like to start there?
Yeah, we can start there just as a refresher.
Great, sure. Yeah, so on the bottom of this page, I've got the circuit diagrams. It's very similar to what we did at the start of day two of class five. Basically, over here on the left, and it looks like we're missing the current arrow, so I'm gonna just add that in. Over here on the left, can you identify if this is a motor or a generator, this circuit at the bottom?
Yeah, more just when you explain as far as going from the exterior to the interior.
Hmm.
Um, so to that's a motor.
Perfect.
Um,
Yeah, and then, regardless if it's a synchronous motor or a synchronous generator, do you remember the relationship we talked about that describes the flow of both the current and the real power P?
yeah, so the current it's supplied to the motor.
Yeah, so if we look at the phasor diagrams and we compare them to the circuit, So we got a motor here on the left, and it's pretty easy to see, right? We've got a bus supplying the motor, and both real power P in watts and the current I, it's flowing from that power supply to inside the stator windings. If we look at the single line diagram, and then looking at the single phase equivalent circuit, that E would, again, that's our bus voltage, our terminal voltage, our power supply, and current and power are flowing from E into the stator windings. It's flowing to EO. And if we look at the generator circuit here on the right, there's a few differences, but you'll notice that the flow of current and power this time goes from inside the machine windings, EO. This time it flows outside to the terminal. So the interesting thing is when we look at the phasor diagrams, power P and current I, they're always going to flow from the leading voltage to the lagging voltage. And that's the whole trick to identifying what machine it is in the phasor diagrams. The circuit's pretty easy to tell, right? We can just look at which way everything's flowing. But if we look up here, so the top three, are these going to be motors or are these going to be generators?
Motors.
Motors, yeah. And how can we tell?
So it's flowing from the E to the EO.
Yep. So this is the direction of real power P and current I. So our motor flows from E to EO, right? If we look back at our motor, it's flowing from E to EO, right? E to EO. And on the phasor diagram, E is the leading voltage and EO is the lagging voltage, right? E to EO. If we compare that same relationship, so D, E, and F are the generator circuits. Now, the terminal voltage E and the internal voltage EO, really the only difference on the phasor diagrams is they're swapping which one is leading and which one is lagging the other. So now we keep E at a reference angle of 0 degrees at all times. It's just easier to analyze the circuit that way. But now if we look at our generator circuits, now EO has a positive angle. So now EO is the leading voltage. And here's the direction of my real power P and my current. It's flowing from EO to E this time. But even though the voltages are trading places, right? Which voltage is sending, which one's receiving power and current. What's true in both cases is it's always going from the leading voltage to the lagging voltage. Does that make sense?
All right. Yeah.
Great. Um, so if you're comfortable there, do you want to talk about the reactive power relationships?
Yes, please.
Sure. So the easiest thing to remember, anytime a machine is overexcited, it's going to supply reactive power. Anytime it's underexcited, it's going to draw reactive power. Regardless of if it's a motor or a generator, that's always going to apply. Overexcited means it's supplying an overabundance of reactive power. It's supplying all of the reactive power that it needs, and then there's a surplus since it's overexcited. So the surplus gets sent outside to the system. True for a overexcited motor and an overexcited generator. An underexcited machine, it's not creating enough reactive power to meet its own needs, right? Rotating magnetic fields in the stator windings, they're going to draw a lot of reactive power. When the machine doesn't create enough reactive power to meet the demands of that rotating magnetic field in the stator, it's got a deficit, right? It's got to bring in some extra reactive power from outside in order to meet the needs of that stator. So if it's underexcited, it's not meeting its own demands. If it's underexcited, it has to pull from the outside grid in order to make up for that deficit. Again, true for a motor or a generator.
Okay.
On the right, can you tell if so C on top is a motor, F on bottom is a synchronous generator. Can you tell if these are both overexcited or underexcited? Do you remember that relationship we looked at in class? How to tell?
The real component of EO being uh, more or less than the output E.
Perfect. Yeah. Um, and that's going to be true for motors or generators. Anytime, so remember,
Okay.
EO is the voltage in the stator windings that's induced from the excited rotor, right? Biggest difference of a synchronous machine compared to an induction machine is we excite the rotors. So now we have a second rotating magnetic field, and that's inducing voltage into the larger stator winding, and that's the EO voltage. So when I think of overexcited, I think of a bigger number. That's when the real component of EO is bigger. It's over the magnitude of the terminal voltage.
So
So
they're both excited, overexcited.
exactly, they're both
Same. Yep.
excited. The real component of EO would be right about here, right? If I make that right triangle. Perfect. So here's the real component of EO. It's bigger than E. That's an overexcited motor. And then if I draw the real component of EO down here for this generator, here's the real component of EO. It's bigger than E. This is an overexcited synchronous generator. So both of these are creating so much reactive power that they've got extra and they're supplying it to the system. So if I look down here, we've got this is a motor, this is a generator. The flow of real power never changes. The flow of current never changes, right? Your excitation only changes the direction of your reactive power. So if these are both overexcited, they're supplying in excess. They've created all of the reactive power that the stator windings need in EO. They have some left over. So now we have whatever's left over. We have reactive power for the generator flowing from the generator windings to the grid. And now when we look at the motor, it gets a little interesting. Again, the motor, if it's overexcited, the rotor is inducing more reactive power than what these stator windings need. So again, we're in a surplus. We have extra reactive power, and that extra reactive power leaves the motor
Agreed.
and flows to the grid.
Okay.
Now, normally when I think of motors, I think of induction motors, right? Induction motors, are they going to lag or lead? Just a standard induction motor. It's gonna what?
Lag.
Yeah, perfect. And it's in the name, right? Induction, I think of an inductor. Inductors draw reactive power. So now an inductive motor draws reactive power. When we talk about a synchronous motor, it can do either. It can draw reactive power or it can supply, export reactive power depending on the excitation. So look at this. So this motor, this synchronous motor, would you think it has a lagging or leading power factor based on the direction of reactive power?
Uh, Lagging. I mean leading. Sorry.
Leading. Yeah. An induction motor will draw reactive power in, and we know an induction motor lags. So if this synchronous motor, when it's overexcited, if it's supplying reactive power, we know it's got to be the opposite power factor. We know it's got to be a leading power factor. So this would be a leading power factor. And then for our generator down here, your power factor terms leading versus lagging, they're going to be opposite for your motor and generator. And it's kind of easier. There was a great post on the student message board, but basically, if I draw a generator connected to a bus, and this bus supplies a motor. So we're gonna ignore our overexcited motor for or the overexcited generator rather for just a second. So we're gonna look at our leading overexcited motor, and that's this motor right here. This motor is supplying reactive power, Q. It's still drawing current and real power, but it's overexcited, so it's pushing Qs out. It's exporting VARs. So we know that this is a leading power factor. If the direction of Q is also flowing in the same direction into the generator,
Do the opposite.
then this is also a leading power factor generator. Is the motor over or under excited in order to supply reactive power? If there's extra reactive power that it's pushing it out to the grid.
Will be lagging, right?
So we're still looking at the leading motor, but what condition, if I go back here, if I look at my motor, what condition results in it supplying extra reactive power? We said this was overexcited, right?
Yeah.
So we've got an overexcited synchronous motor. It's exporting reactive power. It has a leading power factor. What about this generator? If this generator is consuming reactive power, if it doesn't have enough reactive power, is it going to be over or under excited?
Under.
Under, perfect. Yeah. So this is under excited. But the whole thing, if my flow of reactive power is from my motor to the generator, then the whole thing is a leading power factor system. It's like a game of tug of war, right? The system is leading, but the motor is overexcited, so it's pushing VARs out, and the generator is underexciting, so it's accepting those extra VARs from the motor. All of the VARs are flowing up. It's a leading power factor system, but one's overexcited, the other's underexcited. Like think of that tug of war rope. The rope is a reactive power, and it's all being pulled to the generator. Does that make sense?
Yeah.
So if I look at the same simple single line diagram, what happens now? Looking at the motor. If the motor is consuming reactive power, is it acting like an induction motor? Just like induction motors, they'll always consume reactive power because we can't excite an induction motor. What would be the power factor of this motor, my synchronous motor, if it's drawing reactive power in?
Will be
Similar.
under excited and uh, lagging.
Perfect. Yeah. So I know this is a lagging power factor, and I know it's under excited. It's under excited because it's not producing enough reactive power. So it's got to make up the difference and it's going to pull it from the connected power supply. So I know it's under excited. And I know motors, when they draw reactive power, they're lagging, just like induction motors. Induction motors consume 100% of the reactive power they need from the system, and induction motors lag.
Mhm.
So now what about my generator? This reactive power has to come from somewhere, right? So if the generator is supplying that extra reactive power, first of all, just looking at the generator is exporting VARs. Is it
Uh,
over or under excited?
over
Perfect.
excited.
Perfect. Yeah. It's overexcited. It's producing more than the reactive power that it needs. It's got a surplus and it's sending that surplus to the motor. And now look, the flow of reactive power, that game of tug of war, the rope is going from the generator to the motor, right? The generator is pushing everything to the motor and the motor is accepting it. So this generator has the same power factor as the motor, right? That rope, that system, it's all moving in one direction. So what's the power factor of the generator? Is it leading or lagging?
Will be lagging.
Perfect. Yeah, it's lagging. That flow of power is flowing in one direction from the generator to the motor, the reactive power. So these have to have the same lagging power factor.
Oh, okay.
If I have a lagging motor, I gotta feed it with a lagging generator. If I have a leading motor, I gotta feed it with a leading generator. That's that big game of tug of war. That rope is moving in one direction, the direction of the reactive power. So where most people get confused the first time around is an overexcited motor has a leading power factor, but an overexcited generator has a lagging power factor.
Oh, okay. That's what I had on my notes. Uh, and I was kind of confused on that note. Okay. All right. Now I understand.
Good. Yeah, the part that's always the same, overexcitation. Doesn't matter if it's a motor or a generator. Overexcitation, we send VARs. Under excitation, we consume VARs. Doesn't matter if it's a motor or generator. When we talk about is the power factor leading or lagging, then that depends if it's a generator or a motor.
Motor.
Make sense?
Yep.
And the easiest way I think about it, hey, if I've got an overexcited motor that's supplying reactive power, I know it has a leading power factor. I got to supply it with a leading generator. They're both going to lead or they're both going to lag. Make sense?
It does.
Great. You seem pretty good here for the sake of time. Do you want to march on and move to the first?
Yeah. Yeah. Let's go to the first problem. I'm good here. Yeah. Thank you.
Anytime if you're ready to move on, you can tell me right away so we can save as much
Yeah.
time as possible.
Sure.
All right, 11 says, this is from the technical study guide, problem 11. Select the most appropriate relationship out of the choices below that accurately describes the relationship between transformer inrush current and differential protection. Are you familiar with what transformer inrush current is?
Yes, I am.
Great. And we've got a good idea of differential protection.
From the classes, yes, I got um an idea on it. Yeah. I don't deal a lot with the protection, but from your video classes, I was able to understand a little bit.
Good. Yeah, differential protection, it always compares two currents. And differential protection, we're always trying to protect, we're isolating a piece of equipment. So differential protection, most common applications for transformers, a differential protection relay. If here's my transformer and I got a primary and secondary breaker, this differential relay is looking for a fault in the transformer, not outside of it downstream, not way upstream. It's looking for, hey, something in that transformer just blew. You got a phase-to-phase fault, phase-to-ground fault, right? The windings are touching each other. Something's going on. And in order to put the fault out, we need to open both primary and secondary. If I open just the secondary, technically the primary side of that transformer is still hot, which means the secondary side of the transformer is still energized. So if I have an internal fault, opening up just the secondary won't protect the transformer. And we open the primary at the same time to completely isolate it in case maybe there's an alternate power source or, we want to make sure that that piece of equipment, if there is an internal fault, we completely remove it offline by opening the primary and secondary breaker. So that differential protection relay that's looking at controlling primary and secondary, it's comparing how much current is going into the transformer, how much current is going out of the transformer. If I have a downstream fault, the current's going to step up or step down as it flows through that transformer. But if I have a downstream short circuit, the differential relay won't trip the transformer because all of that fault current is flowing through the primary, stepping up or stepping down, and then out of the secondary. Versus if I have an internal fault, you're going to have way more current coming in compared to the current going out. If I have an internal fault, so normally my normal conditions, my current flows from primary to secondary. If I have a downstream fault, my current flows from primary to secondary into that fault. If I have an internal fault, my current is going to flow into the primary, and then the secondary is going to change directions, the secondary line current, and it's also going to flow into the transformer on both ends to feed that short circuit. So then the differential relay is going to go, uh-oh, we got current coming in the primary and coming in the secondary. We got an internal fault, trip it offline. So it's really just noticing the change in current direction on the secondary so that now you got current flowing in to the transformer on both sides, which should never happen, right, under normal conditions. All right, so let's look at the relationship between our inrush current, right? When we first start that transformer up, it's going to draw just like a motor, right? Locked rotor current, inrush current, starting current. Same principle applies to transformers. When that core first magnetizes, it's going to draw a quick, sharp increase until all those domains in the iron core align with the flux. It happens, I don't know, in about 4 to 6 seconds. Most of the current on inrush is flowing just on the primary side for the most part. It's much more prevalent on the primary side of the winding. All right, so A says transformer inrush current is a sinusoidal component typically present only during transformer startup. Okay, so that's true, only present only during transformer startup. That is not seen by the differential protection relay due to being 180 degrees out of phase. So what does it mean for something to be 180 degrees out of phase if I'm looking at the current?
It's flowing on the opposite, right?
Yeah. If I have two currents, right? If one of them is 180 degrees out of phase, then instead of flowing in the same direction, they're flowing in the opposite directions. So would transformer inrush be 180 degrees out of phase? Does the transformer draw inrush current from secondary to primary? Does that make sense?
No.
Nah, no, it doesn't. So we know A is false. B says transformer inrush current does not contain a DC component and can potentially cause a differential protection relay to operate and operate due to CT saturation. Great vocabulary word. Are you familiar with DC component?
Uh, of the transformer or in general?
Just in general.
Yeah,
You are?
yeah.
Have you seen it? We hear it all the
It's
time.
just DC voltage. There's no, yeah.
We see that more common in fault current analysis. Have you ever seen the fault current analysis where you look at the periodic fault current instead of looking at like what's the fault current magnitude, we look at the actual instantaneous signal and the shape of it kind of goes like this. So I've got an AC symmetrical current superimposed on this decaying kind of a flat line. So that's the DC component. This is the AC component. So the transformer inrush, it it does not contain the DC component. So now we got to think, would it potentially cause that differential protection relay to operate because of CT saturation? So remember that differential relay, it's looking for a mismatch of current. It's looking for way more current on one side compared to the other. The inrush current primarily happens in the primary side when that flux first flows, linking the secondary winding. So I know for the inrush current, I do have a good deal of mismatch, but can that transform inrush current? Can it cause CT saturation? Are you familiar with CT saturation?
Yeah, I think you covered it on the instrumentation classes.
It's very similar. Remember the volts per hertz ratio last night at the end of class 5? Very similar to that, right? We're going past the knee curve. In other words, we're
Oh,
maxing
okay.
CT out. The CT core is all of the domains are 100% aligned with the flux. You can't get any more domain alignment out of the flux. Pretty much CT saturation, the CT is overloaded. The inrush current, while it's a little bit higher than maybe the full rated current, do you think it'd be big enough to saturate the CT? And for comparison, fault current. Fault current absolutely can saturate a CT. It's way higher than what the CT is sized to see. So the answer is no. It does not contain a DC component, but it's probably not going to trip your differential protection relay because of CT saturation. The inrush current, it's not big enough typically to cause the CT to saturate, and unless whoever sized the CT made a huge mistake. You're not really going to expect to ever saturate a CT when you're just starting up a transformer. You're going to get some more current when you first start it up, just like you get more motor inrush current, but it's not going to saturate your CT. So we know that B is also going to be false. C, transformer inrush current is linear in both primary and secondary winding, does not result in mismatch differential current. Mismatch differential current just meaning we have way more current on one side of the windings instead of current progressing through it.
Okay. I mean, this the C1 was an easy one. Just the current is linear. I think that was just uh, a no to me. So
Yeah, correct. Yeah, it's not linear because of that DC component. So we already know that half of it is not true. It's not linear.
yeah.
And we know that the inrush current happens more on the primary winding than the secondary. It's mostly concentrated in the primary winding. So we know it does result in mismatch current. We do have an unbalance of current. All right, C is false. Last D, transformer inrush current occurs in the primary winding only. All right, we know that's pretty much true, and can potentially cause a differential relay to operate due to mismatch. What do we think?
So question, Zach. So when they say it happens on the primary winding only, is that really true, or it happens somewhat on the secondary as well?
It's there's probably a little bit in the secondary winding, but it's negligible.
Okay.
If uh, if I were to draw the transformer, even the transformer exact circuit, you know where the parallel core branch is located on the primary side,
Hmm.
that's where this inrush current is happening. Basically, your primary winding gets excited when we apply the voltage. Boom, that magnetic field is created. All of the domains start to align with the flux, and your flux links the secondary winding to the primary. So the primary winding kind of sees the secondary winding as a load. So all that inrush current, that initial surge of current, when the magnetic field is first created, it's just about like 99% concentrated in the primary winding.
Okay.
That
All
makes sense.
right. Yeah, it does.
Cool. What else? Are you comfortable with D being the correct answer? Are you comfortable with the potentially cause the differential relay to operate due to this keyword here, mismatch?
Mismatch. Yeah.
Yeah, it's primarily occurring in the primary winding. The differential relay could potentially see that as, hey, do we have an internal fault? We have way more current being drawn in the primary winding and it's not leaving. We don't have an equal amount of current flowing through it. So we have a mismatch and unbalance of current, which is exactly what the differential relay looks for.
Yeah, and we'll have to have like a setting where it would show the difference between the two currents, the primary and the secondary, in order for it to trip, right?
Exactly.
Like a difference value.
And typically, if differential tripping is occurring during startup because of inrush, here we go, filter. It's a non-linear current because the relationship of those domains aligning with the flux, just like that picture we drew last night when we looked at the volt per hertz ratio, that's a non-linear load. It's a non-linear relationship. So you can have a filter that's going to block everything that's not just a 60 hertz signal. So you can put a filter if your transformer keeps tripping on startup due to mismatch, and it's like, hey, there's no fault here. It's just the standard inrush current. It's what the transformer is going to do when we first start it up. Then you can just put a filter on the primary side of that differential relay. So it's like putting a horse blinder on it. The differential relay won't ever see just the startup inrush current. But if I have a fault, it'll still be a 60 hertz signal for the most part. So I'll still see a mismatch due to a fault.
Okay. All right.
Makes sense?
Yep.
Cool. Ready to march on?
Yep.
All right, march on. 13. We'll be covering, so harmonics, we're going to be covering just about everything on this problem on class 10 applications. But yeah, this question, you got to be familiar with positive, negative, and zero sequence harmonics. So let's see, select the most accurate statement below. Describes the effects of negative sequence harmonics. So we're trying to identify A, B, C, or D below. Which one is describing negative sequence harmonics? Are you familiar with positive, negative, and zero sequence harmonics?
Not the harmonics, no, I'm
So
not.
quick crash course, and this is exactly what we'll go spend much more time on class 10. So if I have a positive sequence harmonic, that means the order of my phases, assuming I've got a positive system, then my positive sequence harmonics are also going to be ABC order. Negative sequence harmonics are in the opposite phase rotation. Three-phase system, I only have two rotations, right? Either ABC positive sequence or ACB negative sequence. So our negative harmonics are going to be ACB sequence. It's the opposite phase sequence compared to my 60 hertz fundamental system. And then zero sequence harmonics, they all have the same phase angle. So I'd say theta A0 equals theta B0 equals theta C0. They're all the same angle. So here's what happens. If I already have a positive sequence system and I add another signal on top of it, it's going to be a harmonic. So my peaks, my maximum peaks and minimum peaks are going to probably occur more often instead of just, it's not going to have a 60 hertz frequency, right? It's probably going to have a faster frequency. But if it's still in the same phase sequence as my fundamental, do you think the signals will add or will they subtract if it's that same ABC sequence?
Oh, at
Yeah, they'll add. In other words, if I've got two sine waves and they're both like this, right? The peaks line up. Two of them, they're going to add up, right? It's going to be like two times, right?
Mhm.
They're going to be we call this additive harmonics. What about my negative sequence? If my fundamental,
They'll subtract, right?
perfect, they'll subtract. Um, and the way we can show that is look, if my peaks and valleys occur like this, that's negative, right? That's positive. That's negative. That's positive. They're going to subtract each other. So these are subtractive harmonics. Zero sequence gets really interesting. Typically, a balanced system. What's my neutral current equal for a balanced system?
Zero.
Zero. Yeah, because all of the phase angles are 120 degrees apart. So when we add them, right, Kirchhoff's current law, when we add them at the neutral, it adds up to zero, just like we did on a class two circuit analysis. What happens if my system is not balanced? Do I still have a zero neutral current?
No.
No. If I've got current on phase A, B, and C, they're not 120 degrees out of phase. Instead, they're all in phase with each other. What happens when they get to the neutral?
It they'll have you'll have current and neutral, right? Different
Yeah.
zero.
So if I've got my neutral, and I've got A, and I've got B, and I've got C. And right here, if I wrote Kirchhoff's current law, right, I'd say the neutral current leaving
This will be
would
the
be the
sum.
sum of A, B, and C, right?
Correct.
What happens if all of the angles on A, B, and C are the same? What happens when I sum them up at the neutral?
Yep. It'll be zero, right?
Not quite. It'll be zero when they're 120 degrees out of phase. So if I wrote, okay, Kirchhoff's current law, my neutral current, I've got, I don't know, maybe 1 amp 2 amps, and 3 amps, but if they all have the same angle, maybe it's 10 degrees when I add them up,
So
then what happens?
we
Then I just add the magnitudes, 3, 5, and
oh we
6.
took yeah
They'd all they would all sum at the neutral, right? If they
three
all have
times of the magnitude plus the degree, right?
Yeah, if they all have the same angle, then all I'm doing, I'm just adding magnitudes at that point.
Mhm.
So your zero sequence harmonics, these are going to sum at the neutral. All right, let's see if we can use these three relationships. And again, we're going to go through a much more in-depth explanation of this on class 10 later in the semester. But let's see if we can answer A, B, C, and D based on those relationships for positive, negative, and zero. Remember, we're trying to identify A, B, C, or D. We're trying to find, this should be red, we're trying to find the negative sequence harmonics, which we know are subtractive. They're gonna counteract any current that's already present on the system. All right, so A says negative sequence harmonics sum at the neutral. Which harmonics sum at the neutral?
It's the zero.
Perfect, yeah. So it's not A. A is describing zero sequence. B says negative sequence harmonics circulate between phases and can lead to overheating conductors due to their
And
ad.
if so, that's false.
That's false. Which harmonic does this describe?
It's the positive.
Perfect. Absolutely. C, negative sequence harmonics oppose the rotating magnetic field in motors, can cause motor windings to overheat as the motor draws more current. So let's think about this. If I have a rotating magnetic field, right, in the motor,
Mhm.
if I have negative sequence harmonics, they're going to be subtractive, right? They're
Correct.
gonna they're gonna subtract from it's gonna essentially decrease artificially the system line current. So that magnetic field, what creates that magnetic field? What's directly proportional to a magnetic field? It's current. What happens if I decrease the current? What happens to the magnetic field?
Will decrease.
Magnetic field's also going to decrease. That magnetic field is what creates the torque in our motor. If I decrease the magnetic field, we're opposing the rotating magnetic field in the motor, right? We're weakening that magnetic field. Um, Classic real life condition, classic qualitative problem for the P exam is under voltage conditions for motors. If I supply a motor with not enough voltage, it's actually going to draw more current, right? In other words, the rotor is saying, hey, I don't have enough torque from this rotating magnetic field. So it's going to draw in even more current from the power supply to try to puff that magnetic field back out to where it should be to operate that load. And when that happens, uh, it's going to overheat the motor windings, right? Motor windings are only rated for so much current. So what do you think about C?
So that would be true, right?
True. Yeah, this is the answer. C is describing our negative sequence harmonics. And then how about D? So this says unlike triplet harmonics. Are you familiar with triplet harmonics?
No. Hmm.
For now, all you got to worry about, and we'll explain this later on in class 10, triplet harmonics, they're just a specific type of zero sequence harmonics. It's the most common zero sequence harmonics. Computers, power electronics, they mostly draw triplet harmonics. Triplet, it's just a subset of zero sequence. So everything that applies to zero sequence, they're additive at the neutral, applies to triplet. So D says, unlike triplet harmonics, negative sequence harmonics are not harmful to the electrical system since they do not contribute to the total harmonic distortion of the system. What do we think about that? Is negative sequence, is it not harmful at all?
That's uh that's false.
Yeah, it's also false. It's totally false. We already identified subtractive, subtractive harmonics hurt rotating magnetic fields. They are going to weaken transformers, weaken motors. Additive, we're gonna overload our system conductors. Zero sequence, we can overload the neutral conductor. Does that make sense?
Yep.
Great. Ready to move on?
Yep. Sure.
Now we'll see how many more we can knock out. And then 13 just summarizes exactly what we talked about. Um, Look, here's our zero sequence harmonics. Notice it's pointing in the exact same direction, right? They're gonna sum up at the neutral. Positive sequence harmonics, like A, B, C. It's in the phase rotation is the same order, assuming we have a positive sequence system. And then negative sequence harmonics, instead of B, now we have C lagging A and B lagging C. So that's the opposite phase sequence rotation. All right, let's check out 29. So this is very similar to the problem we did last night in class. So let me know if we can still do it, or if you'd rather move forward, we can move forward too. It's totally up to you.
Yeah, we can just touch on
We can
this.
also still look at it too if you'd like.
Yeah, we can look at it.
Okay.
Uh,
So we've got a single phase, uncontrolled half wave rectifier. What kind of rectifier or what kind of switch makes an uncontrolled rectifier?
the diode,
Diode. Yeah. Single phase, so I only have one AC input. Half wave rectifier, how many diodes do I have?
only two.
Close, just one.
Oh. So you
So
have one. Sorry. Yeah.
yeah, just one. We're fed from 120 volt RMS AC power supply, providing power to a DC load. Aha, look at this. The ratio of the peak to peak ripple voltage to the maximum AC voltage is 11%. In other words, you're saying your delta VO, your peak to peak ripple voltage, compared to your maximum voltage, this is just like that example last night, is 11%. They're asking determine the minimum DC voltage seen by the load. So the output is going to look something like this. It's going to be that capacitor is going to sit there and charge and discharge, charge and discharge. Remember that graph from last night? So they're asking, okay, if I know the ratio of our peak to peak ripple, delta VO, compared to the maximum voltage, can we determine the minimum voltage? All right, let's take a look at the solution. Solution is great because the circuit will really help us walk through this. So here's our single phase, uncontrolled half wave rectifier, just one diode. And here's our filter or smoothing capacitor in parallel, or remember that keyword shunted to the output. So first of all, we're going to use this formula in the reference handbook. Here's our peak to peak ripple voltage, delta VO, equals maximum voltage divided by frequency times the resistance, that's just the DC load, times the capacitance of that filter capacitor in unit of farads. So if I want to use this, I got to figure out what's my maximum voltage first, right? Does the problem give us the maximum voltage?
Just the RMS value, so we need to calculate it, right? Yeah.
Yeah. How do we convert from RMS to
Just
maximum?
multiply square root of two. Yeah.
Multiply by square root of 2. So here's our input, 169.7 maximum volts, right? This is the square root of 2 times 120 sine omega t. So that's our AC input that we're feeding to our half wave uncontrolled single phase rectifier with a smoothing capacitor. So now we've got VM. Let's see, the problem didn't give us 60 hertz. P exam, test on North American standards. Anytime you need frequency, if you're not given to it, we automatically know, hey, it's going to be a 60 hertz input, right? Um, so we want to see the minimum voltage. How would I calculate the minimum voltage here?
just the difference between the VM minus Vmin.
Perfect. Yeah. I can say Vmax equals, how about
Delta V.
delta VO plus Vmin,
Correct.
right? This amount plus this amount equals that total amount. So great. So we just figured out Vmax, right? We're trying to solve for Vmin.
Yeah, yeah, we can just use the equation and solve for it.
Yep.
All
Perfect.
right.
Good.
All right. That's good.
Move on. All right. Yeah, remember from last night, this formula is not in the reference handbook, but if we look at the graph in the reference handbook, it's pretty easy to tell, okay, peak to peak ripple plus Vmin has to equal Vmax. That's where that relationship comes from.
A quick question, Zach. The R and C values on that formula, if you go to the next first, yeah, the R and C values, those are the condensing capacity, and R will be the resistance.
Yeah. So I'm gonna just copy. So here's that formula. The C value is the value of this capacitor in
Mhm.
unit of not ohms, careful, it's a common mistake, in unit of farads. That's
Uh,
capacitance in farads. And then your R value, this is really just your DC load.
oh, okay. All right.
That's all. That's your DC load. And we didn't even need it in this problem to solve.
Yeah, yeah.
We're just,
I'm just wondering for like future if they
sure.
instead of giving me the delta V, they give me the C and R value if I can use them to
Yeah.
calculate.
And
All
if
right.
you want more practice on this one, retry that same in class. We did a very similar example in class where we did the ratio of delta VO to VM, and we solved for C using the 60 hertz frequency and the given DC load, and we solved for the capacitance.
Okay. All right.
All right, 11:52. We'll see if we can knock out these last two. So we also looked at this one last night. Let me know. Would you like to still?
I, yeah, I think we can skip this one because I this one what you explained yesterday. Yeah.
Sure. And then, yeah, I know this problem was important for you, right? You wanted to talk about how we can determine which
Yes.
ANC numbers go where.
So yeah, again, I'm not too familiar with protective relays. I was just looking at where when we use like a CT or a PT, and yesterday I did went over your slides and all the protective relays and kind of understand when we need a current or a voltage relay,
Okay.
and you know
So
that
here's
makes sense.
here's page 38 of the reference handbook. These are the only ANSI device numbers they give you. We've got the first one, 87. That's our differential relay. So if I'm looking at this single line diagram, which one do we think the differential relay is going to be? Very
That
simple.
will be in between the transformers, right?
Perfect. Yeah. Here's 87T.
Yeah.
Um, all this T stands for, this just says we got an 87 differential relay and it's protecting a transformer. That's all. So another giveaway, your differential relay, you always have to have two CTs because here's the transformer primary current flowing into the transformer. Here's the transformer secondary current. So the primary CT steps down the primary transformer current, feeds it to the relay. The secondary CT steps down the secondary transformer current, feeds it to the relay. That's how it's looking for any internal fault. Biggest
Yeah.
giveaway, um, differential protection. You can also see it a lot of times protecting a bus. If I have a big substation, you might put a differential relay on the primary of the main, on the load side of the main breaker, and somewhere on the secondary. So a really big bus, Sometimes too, you might do differential protection, but transformers, big transformers almost always have differential. Because if I have an internal fault in the windings, I can't just open the secondary. I got to open both.
Hmm.
Let's see, 52, ANSI 52,
That'll be the breakers.
circuit breaker. Yeah. Which ones are the circuit breakers?
Will be the primary and the secondary
Yeah.
transform.
A lot of times you'll see like 52-1 and 52-2, just saying, hey, this is ANSI circuit breaker, breaker number one. This is an ANSI circuit breaker and it's breaker number two. Or maybe 52 dash transformer P for primary and transformer S for secondary, or transformer one, transformer two, T1, T2. This is the ANSI number, and then this would just be like the name, the internal name of that breaker, like the client name, the plant name.
Hmm.
51, one of the most common types of relays.
Yeah,
Uh,
it's the inverse, the
yeah,
51 and 50.
yeah, 50 and 51 are going to be your most common. If I'm looking at here, I got two left. This relay gets a CT and it gets a PT. Would an inverse time overcurrent relay or an instantaneous overcurrent relay, would that ever get a PT, a voltage signal? If we're just,
Just to,
yeah, we're just getting we got one CT. This is going to be inverse time, or this could also be instantaneous. So this just says, hey, this is this is time over current for the generator, right? And really, this G could also be for the ground. What do you think this is looking at to protect against? If it's between the
from fault.
ground fault. Perfect. Yeah, that's just protecting the generator from ground faults. And then last one, 67. This is AC directional overcurrent relay. So process of elimination, I know this has to be the directional overcurrent. First of all, if I'm protecting against overcurrent, what type of instrument transfer do I need?
Current, the CT.
CT, yeah. Now I can figure out how much current I have on the line. And now look, directional overcurrent. This arrow means that, like, this is a generator, right? This generator wants to supply real power P and current I to my generator bus, right? We want to avoid this a condition called motoring. If this generator, the generator can supply or consume reactive power all day long. But if this generator consumes current and real power P, this is called a motoring condition. This generator is going to start spinning in the wrong direction. It's going to act like a motor. Really dangerous. You're going to damage your generator, all sorts of safety issues. So this current arrow says, hey, as soon as you have a current flowing in this direction, we're going to trip the generator offline. So I know I need a CT so I can measure the current. How do I tell what direction the current is flowing in? What other kind of signal do I need?
Active power.
How about this? Let's say this is here's my voltage, right? We'll use an angle of 0 for my voltage. What's the difference between, we'll say it's a lagging system. What's the difference between this current and this current?
180 degree.
Yeah, 180 degrees. I know that this current is flowing what? It's flowing backwards, right? What do I have to compare these two currents with to know, hey, which one's flowing in the normal direction, which one's flowing backwards?
Uh,
And remember, when we draw a phasor diagram, it's like a snapshot in time. In real life, these phasors are rotating 60 times a second for a 60 hertz system.
the the angle of the current power
Sure.
factor.
So if I know this current angle and I know this current angle, how do I know which of these two angles results indicates a backwards current? I got to compare it to what other angle?
Oh, to the voltage
I got to compare it
referencing.
to my voltage angle. because then I know I know we'll draw it this way. Then I know my power angle, right?
Mm.
So if I want to tell what direction the current is flowing in, I also need to pull in a voltage signal from a potential transformer. And all this lets me do is compare, look at the phase shift. If the current flows into the generator, if the current flows backwards, my voltage isn't changing. So now I've got a current that's, lagging my voltage a little bit, depending on the power factor of the system. And then all of a sudden, I have an angle that's way different than the voltage angle. It's way greater than plus or minus 90 degrees compared to my voltage angle signal. I know I've got a backwards flowing current. We got to trip that generator offline to protect it. Does
Okay.
that make sense?
Yeah.
If I'm just looking at the current signal, like the CT, like this 51 relay, it has no idea what direction the current's flowing in. It's just looking at the magnitude. It can see the angle, but it has nothing to compare that angle to. So remember that angle again, it's moving, it's going from 0 to 360 degrees. It's doing that whole rotation 60 times a second. So without a voltage input signal, we have no way to compare how far or how close to that voltage signal it is. We have no way to tell what direction it's flowing in. But if I'm
Well,
just tripping on overcurrent, all I need is I'm just looking at the magnitude over here.
yeah. So in that case, the 67 relay, would that send a signal to the generator breaker to trip?
Yeah, absolutely.
So, okay.
Yeah.
So do we need to show a 51G or a connection to that 51G as a dash line?
So we wouldn't show it to the 51G. We'd probably show a dash line to 52.1.
Mm.
52.1, look, this 67 would probably trip. So this is
Down.
the primary breaker for the transformer, but this also acts as our typically call them a GCB for generator circuit breaker. This is the breaker that will sync this generator to the grid or open and disconnect it to the grid. So
Oh,
yeah, if I clean this all up really quick, if I clean that up, here's 51, 67, 87. You could probably show, yeah, we're not showing none of the trip signals are being shown, but we could probably just show them like this. When you look at a single line diagram, the trip signals aren't always shown because you can typically assume which breaker it's going to trip, or the relay might have the same suffix as the breaker it's going to trip. And then look, if I were to show the 87, the 87 would have a trip signal to 52.1 and to what?
52.2. So
Yeah.
67 will trip both 51G and 52.1 in this case? Or just 52.1?
So there's only two devices on the single line that we can actually trip. We only got two overcurrent protection devices. We've got 52.
Oh, yeah, sorry. Yeah, yeah.
So
Yeah.
this guy,
It's just a relay. Yeah.
if he
Mhm.
detects ground fault current in any direction, this signal gets hot, we send a trip signal to 52.1.
I got it now. Yeah, sorry.
No problem.
Yeah.
And yeah, we'll finish it like this, like uh
I was looking 51G as a breaker.
as a breaker. Yeah, no,
Yeah.
no worries. All
Yeah.
right. What else? I think we got perfect.
Yeah.
We're just about 1 hour. We got through every question, which is fantastic.
Thanks.
Awesome. How does this
Yeah.
help? Does this help kind of clear up some of the concepts?
Yeah, help a lot.
Good. You got,
Appreciate it.
yeah, my pleasure. You got any questions before we go?
No, I
Pretty
think
good.
I'm all set.
How's everyone
Thanks
doing
for
the
your
chat?
help.
How's everyone doing the chat? We got about a small group you. We're tuning in. Bishoy asks, is this the same thing as 32 reverse power relay? Yeah, you're 67. very similar to reverse power, except we're just tripping on directional current to prevent motoring, where reverse power, you're looking at the reverse flow of power. More or less kind of the same. They achieve the same thing. If I've got current flowing backwards, I also have power flowing backwards. Good. See just about everyone enjoying it in the chat. All right, Lewis. Well, yeah, that's it for today. I'll shoot you an email when we get this posted on the YouTube channel if you want to revisit the recording at all. But yeah, man, keep up the hard work. You've been killing it in class, and yeah, keep posting. Anytime you're studying, just keep your phone in your hand. If you have any questions, just snap a photo. You can always post it right to the student message board. So keep asking questions and keep
All
up.
right. Thank you.
All
Thanks,
right,
Zach. Appreciate it.
my pleasure. We'll see you.
All right. See you.